Hello, my name is Maria João Sousa, and I will present a RASite project developed with Alexandre Moutinho and Miguel Almeida in a collaboration between IDMEC and ADAI in Portugal. The project is about the development of an autonomous multimodal robotic perception system for intelligent wildfire detection and monitoring. This presentation has 5 parts. First comes the introduction and motivation. Second, the project objectives will be presented. Third, we present an overview of ongoing research activities. In the fourth part, we will discuss the progress so far and upcoming work. And at last, we will close with some concluding remarks. As we have been witnessing in the last few years, the effects of climate change have been aggravating wildfires in several regions worldwide. In Portugal, this problem has dire impacts on communities, especially in rural areas where populations are more vulnerable since emergency response means are not as readily available as in urban contexts. Since fire events are becoming more frequent and severe, fire detection systems are crucial to identify fires in an early and controllable stage so that these impacts are mitigated. To that end, with the need to attend to extensive areas, unmanned aerial surveillance can have paramount importance for decision support in wildfire operations. Particularly, due to their high mobility, these platforms can provide data with high spatial and temporal resolution concerning the risk areas, such as the wildland-urban interface. For this reason, our research has been focusing on developing multi-robot systems composed of high-altitude balloons and drones that can provide real-time Earth observation. In that sense, high-altitude balloons can act as pseudo-satellites, enabling monitoring and deployment of unmanned aerial vehicles. Then, teams of UAVs can cooperate to satisfy mission tasks in dynamic environments, being equipped with computing capabilities that allow multimodal perception and intelligent inference. Can also complement ground sensors used for risk assessment. In this context, our RAS-supported project aims to develop a robotic perception system for airborne platforms for early detection and monitoring of fire events. The research partners are IDMEC and ADAI. IDMEC, namely the Center of Intelligent Systems, currently investigates innovative solutions for wildfire decision support systems in the scopes of autonomous robotics and computational intelligence. ADAI, through the Forest Fire Research Center, is an international reference in wildland fire research with unique experimental structures that enable laboratory testing and field trials. In this project, the objectives are to develop a multimodal perception system to complement different sensing ranges, the synchronization of image sensor triggers to log orientation and georeferencing data, in turn enable the real-time processing of high-dimensional data on board with GPU-enabled embedded computing, and most importantly, do all this through the design of a light payload with low power requirements so that it can be integrated on board aerial platforms. The platforms that can be used for testing the developed sensor payload are a small DJI F550, mainly considered for indoor testing. Also, DJI S900, which is a professional-grade heavy lift drone, which can accommodate a heavier payload for a longer flight time. And also a sounding balloon, a high-altitude platform, which can ensure 2-hour flights and coverage of extensive areas on the ground. Recalling we need to design a light sensor payload, the following components are selected. Jetson Nano board for onboard computing with GPU, Pixoc flight controller with internal IMU and external GPS, which is useful for data collection and for trigger synchronization. A FLIR view PAW to capture thermal images, and a visible range Z-Mini stereo camera. As specified, all components have low weight and power consumption, yet with powerful sensing and computing capabilities. The software frameworks used on board are built on Ubuntu and are based on ROS middleware. The image pipelines are built with OpenCV, and intelligent algorithms are implemented using TensorFlow. The bridge between ROS and Pixoc is done through the Mavros package using the PX4 stack, which enables the image capture synchronization and registering the inertial and GPS data. For the intelligent fire detection algorithms, we use different approaches for visible and thermal image data. For visible range, since we can source a lot of data online and from existing public datasets, we have applied deep neural networks based on convolutional layers for feature extraction. Our training dataset is based on real wildfire events and field trials and is described in detail in a previous publication. The main advantage of this approach is it is able to achieve high performance based on raw data and learning of scene context, while the main disadvantage is that the models lack transparency, which prevents effective fine-tuning. To complement this approach, we have implemented for thermal images a different intelligent systems approach. It is based on specially designed feature engineering, which we have also proposed in previous work, and which consists of extracting a set of color baselines to identify when a fire is present in the scene context. Then a data-driven clustering-based fuzzy model is created, capable of identifying situations with fire and without. The main advantage is that once the model is designed, it is easy to implement this type of low complexity rule-based systems, and it also has low computational load. The main disadvantage currently is that datasets of thermal images in fire scenarios are still limited. To overview the progress achieved so far, we can see that from the tasks and activities already carried out, we have already performed the sensor payload development as presented here before. We also developed intelligent algorithms for different data modalities, which are exemplified for a fire experiment in the lab in Lausanne on the right. We have also done the integration of these solutions on board regarding upcoming tasks. Next, we will perform further field trials and validation of the proposed system, and subsequently the results dissemination. Current challenges are the COVID pandemic, which slowed down progress in the lockdown months and is causing a lot of uncertainty about the next few months, as well as the need for favorable weather conditions to perform the tests and formal authorizations to perform the flights, which is also difficult to manage due to the unpredictability of the weather conditions. To conclude, I would like to revisit some highlights of this project. First, the multimodal solutions. We have been developing using visible range and thermal cameras. Second, the novel intelligent algorithms for fire detection that we are continuously developing as we build larger data sets with rich information. Third, the actual implementation on board, which is a significant step forward. Our future work, as I mentioned, still concerns further testing and field trials, preferably in experimental birds, and also results dissemination, which is very important for us too. To conclude, I am available to answer any questions. I want to give a special thank you to the RASite group for the support in this project. Also, I would like to mention Project Eye in the Sky, which is started this year and is enabling many research activities in this topic. I invite you to check out our website for more information on our developments and field campaigns. We also acknowledge FCT for the support grants for this research. And at last, thank you very much for your attention.